All right, welcome back. So in videos 1 to 3, we went over the simplified version of solving the roller coaster track problem. In these videos, we had a block moving down the track and we ignored friction. To make the roller coaster track problem a little bit more challenging, let us now have a ball that is rolling down the track with friction. Just like with the block, we are solving to find the minimum height that the ball can be released from in order to make it through the loop. To start this problem, let us draw a diagram of what this track looks like. We will have a ball at the top of the ramp initially. Then it will roll down the track to the final point of observation at the top of the loop. When drawing the path of the ball, since it is rolling, we need to take into account the radius of the ball since we have rotational motion. We must take into account that the center of mass due to rotational motion will be the center of the ball. So we draw the path of the ball at the radius on the ball all the way from the initial to the final position of observation. Now that we have the diagram for the motion of the ball, let us draw a free body diagram of the ball at the top of the loop. There will be two forces acting on the ball, the normal force and the gravitational force. Can you draw where both of these forces are going to be? Both of the forces will be in the y direction, but we're going to say that the center of the loop is in the positive direction, and both of these forces point towards that center of the loop, so both of these forces are positive. Now, if we sum the forces in this y direction, we know that they will be equal to the mass times the centripetal acceleration from Newton's laws. Since the ball is at the top of the loop, the normal force will be 0, leaving just a gravitational force equal to the mass times the acceleration. Now we want to solve for the velocity at this point. We know that centripetal acceleration is equal to the velocity squared over the radius. In our case, the radius will be the radius of the loop, so we're going to denote that with big R. This gives us that the velocity of the ball is the square root of the acceleration due to gravity times the loop radius. Now that we know the velocity of the ball, let us write down the conservation of energy equation. We have that the initial kinetic and potential energy equals the final kinetic and potential energy. For the left-hand side of the equation, the initial kinetic energy is going to be 0 since the ball is being released from rest. The initial potential energy is going to be mgh, where h is the height that the ball is going to be released from. We will have a final potential energy of mg times 2r, since we want to make sure the ball can make it through the loop, so the height is going to be twice the radius of that loop. That's why that 2r term comes from. For the final kinetic energy, we will have both final linear and final rotational kinetic energy added together. To find the final kinetic energy, we want the final linear kinetic energy, which is 1/2 mv squared, plus the final rotational kinetic energy, which is 1/2 I omega squared. I is the inertia, or you can think of it as the rotational mass of the ball, and omega is the angular velocity of the ball. Now, we can simplify this by using the linear portion, that 1/2 mv squared term, and substituting in the velocity that we found before. The square root of gr is just gr, so that's where that gr term comes from. The inertia of the ball is 2/5 times the mass of the ball times the radius of the ball squared. And the rotational omega, so that angular velocity, can be converted to linear velocity by taking the velocity and dividing it by the radius of the ball. This will all need to be squared as omega is squared in the original equation. With all these substitutions being made, the last thing to do is to solve for the height at which the ball needs to be released from. Since all of the components of the energy conservation from the previous slide had mass and gravity, that can be canceled out. This leaves us with an equation of only height, the loop radius, and the ball radius. With some algebraic simplification that you can follow using the equations on the previous slide and the slide shown here, we can get that the height that the ball needs to be released from is 27/10 times the radius of the loop. Now, let us try releasing the ball from the height that we just solved for, and let's see if the ball will actually make it through the loop or not. All right, so now that we know what height we need to drop the ball at, let's give it a shot. We're going to drop the ball out from a little bit of a higher height since we're now accounting for rotational motion. So we're going to drop the ball off from a height that's 2.7 times the radius of this loop. All right, here we go in 3, 2, 1.
And now we see that the ball did make it through the loop. And before we end off, here's a little physics joke for you. Why can't we trust atoms? Give it a minute. You have an answer? All right, okay. It's because they make up everything.